Imagine if you could watch the moon over the course of several weeks. You would see that light would gradually be added to the face of the moon, and then after reaching the full phase, the light would seem to come off. So these are the familiar phases of the moon. Now, before we describe the phases of the moon, let's just clarify one rather important point about the moon, and that is we always see the same side of the moon. It doesn't matter what phase it's in. If you look at the features on the moon's surface, we're always seeing the same near side of the moon. So a really good way to compare the near side and the far side is to look at them side by side. You notice that the near side has these light regions, but also many darker regions. These are known as mare, and the far side is dominated by highland regions. So the question now is, why do we only see one side? Well, we will eventually learn that this all has to do with something called tidal forces. But practically, what does it mean to only see just one side of the moon? Let's take a simple illustration. I've rendered the moon with the far side in gold and the near side just as the normal coloring of the moon. So we have the Earth at the center, and if we could imagine for a moment the moon revolving around the Earth, but we're going to let the moon stay still. In other words, we're letting the moon revolve, but we're not allowing it to rotate on its axis. So if the moon doesn't rotate on its axis, then over the course of about a month or so, we should expect to see all sides of the moon, both the near side and the far side. On the other hand, if the moon executed several rotations on its axis as it revolved around the Earth once, then we would also be able to see both the near and far sides of the moon. So how is it that we can only just see the near side of the moon no matter where it is in its revolution around the Earth? And the answer is timing. The rotation period is exactly equal to its orbital period. So you see that as the moon is revolving around the Earth, the moon is also executing a single rotation on its axis. And this keeps the near side of the moon facing the Earth throughout the entire lunar orbit, and we call this type of rotation synchronous rotation. And it's for this reason that we always see the same side of the moon facing the Earth. Therefore, the far side, by definition, is forever hidden from our view. As we saw in the previous images, if we wanted to actually view the far side of the moon, you have to go there, or at least send a spacecraft there to take a picture and send it back. Now let's take a more realistic view here. So we're going to put ourselves in space, and you notice that we have both the Earth and the moon has a daytime side and a nighttime side. But as the moon executes its rotation around the Earth, we can only see at any given time a portion of the near side because of the illumination from the sun. So let's just imagine for a moment you're standing on the Earth and you're looking toward the incoming sunlight. And suppose the moon just happens to be between the Earth and the sun in this case. So we're looking at that first image of the moon that is to the right of the Earth. If we were to look up, take a look at the moon and somehow squint and be able to actually see the moon, which we never could really expect to do, we wouldn't see a moon. The moon would be in silhouette, and we call this phase of the moon the new moon phase. Likewise, the appearance of the moon is purely the result of where it happens to be in its orbit with respect to the incoming sunlight. And so you notice that the phases where the light is being added to the moon, we call those the waxing phases. Whereas when the light is being removed from the moon, we call those the waning phases. So we have waxing crescent through first quarter to waxing gibbous to full, and then we repeat the cycle, but we reverse it. We go from gibbous to third quarter to crescent and then back to new again. So let's imagine that we are now standing in place of the Earth, and that is the main view that we see here. We're starting out with the moon between us and the sun, so therefore this is new. If you look at the inset on the lower left of your image, we have the Earth and moon, obviously not to scale, but certainly within the same configuration. We have the Earth and then we have the moon, and you could see the sunlight is illuminating both the Earth and the moon, and the sunlight would be coming in from the right. So let's begin the movie. Let's just watch the moon revolve around the Earth through one complete lunar cycle. So here we're in the new phase. We simply don't see the moon, but you notice that as the moon makes its way to about the 1 or 2 o'clock position in the inset, we're beginning to see just a little sliver of that illuminated side. So this is the waxing crescent. Now, when the moon gets to about 1/4 of the way around in its revolution around the Earth, we call this phase first quarter. A lot of times people call this the half moon, but in fact we're seeing just, well, 1/4 of the moon's entire surface. So the moon is continuing to move beyond first quarter. It's not quite full. We call this phase waxing gibbous. Now you see as the moon is coming around to basically opposite the Earth from the sun, we can now see the entire illuminated near side of the moon, or rather the entire near side of the moon is fully illuminated. We call that the full moon phase. So as the moon begins to come around, it's losing some of that light as seen from Earth. We call this waning gibbous. And as the moon makes its way about 3/4 of the way around in its orbit, we give it the unimaginative name of third quarter. So the moon has gone 3/4 of the way around in its orbit, and we are seeing just 1/2 of the near side of the moon. You notice, if you look carefully, you'll see that there still is a near side of the moon. The moon didn't disappear, it's just that it's in silhouette. So now we're in waxing crescent, and the light continues to wane off the moon, so to speak, as seen from Earth, until we eventually come around and we lose the very limb of the illuminated side, and we're back to a new moon phase once again. Now, as we think about how long this takes, well, the answer is it's about a month, but about a month is really the key phrase here. Let's explain how this works. So we have a diagram of the Earth and Moon, and we see the Earth's orbit illustrated, we see the sun. And I'm also going to point a reference to the vernal equinox, and we're just going to imagine the vernal equinox as a fixed location among the stars, and we will be able to measure our position relative to the vernal equinox no matter where we are in our orbit. So in this illustration, I've chosen to place the moon on the left, and that would mean that we're looking at the moon and we see the fully illuminated side of the near side of the moon. So we have the full moon, of course. But imagine what would happen if the moon were to make one revolution around the Earth. Well, it can do that, but at the same time, the Earth is also moving about its own revolution around the sun. So when the moon comes back to its starting location with respect to the vernal equinox, it isn't quite full yet. It's almost full, but it's not quite full. It's now a waxing gibbous phase moon. So this period of time is called a sidereal month, and sidereal literally means the stars. So this is a month with respect to the stars. It allows the moon to make one full revolution around the Earth. This comes out to about 27 1/3 days. That means if we want to get back to our starting phase, which in this case was the full moon, well, then we have to allow the moon to orbit and indeed the Earth to orbit a little bit more. So we need a couple of extra days of motion, and this gives us what's called a synodic month or a solar month, literally with respect to the sun. So this is what gets the moon back to the starting phase. And it wouldn't matter if we chose the new moon phase as our start phase or first quarter phase as our start phase. From any given phase to any given phase, it's going to take 29.5 days to get there. So there's a difference. When we say a month, the first question we have to ask ourselves is, well, what do we mean by month? So let's imagine the phases. Now we're going to take a split screen view, you might say. We have the Earth and the moon on the left. We have the phase of the moon as it appears on the right. And you notice I've drawn a symbol representing the direction to the sun and a second symbol representing the direction to the vernal equinox. So we start out with the new phase and we proceed to the waxing crescent as we saw. And again, now we're just repeating what we saw before, but with a slightly better understanding of how these phases evolve and the sequence of the phase. So the main reason for the phase is simply an alignment or a geometric view of the moon with respect to where it happens to be with respect to the sun. So let's put all this together, and now we're going to imagine ourselves looking at the moon. I'm using stellarium, and I've zoomed out to a very wide field of view, which is way beyond what the human eye normally sees. The moon and the sun are going to be very tiny in the sky, so I correct for that by enlarging the moon by about 10 times. Now let's take a look at our inset. So this is a overhead view. We're kind of looking at this slightly in perspective. Our hometown of Baltimore is right there, and that means that north is toward the top of the globe, south is toward the bottom, east and west to the right and left accordingly. So because the Earth is rotating on its axis, that means that the sunlight is coming in from the direction indicated, and that means that given our location, we're kind of rotating from the night side of the Earth into the daylight. We are therefore experiencing dawn. And so the sun is exactly where we expect it to be. It's on the eastern horizon, it's just rising. And because the moon is between the Earth and the sun, the moon is presently at the new phase. So we have our vernal equinox. We know that the Earth is going to continue in its orbit as the moon revolves around the Earth, and we're seeing the moon in the new phase. By the way, I've just gone ahead and just added that dotted line just to help us see the moon. Let's go ahead and get the movie started, and we'll just watch and see what happens. So we notice that the Earth is rotating. It's carrying us from the daylit side to the nighttime, and we come back to a new day. But because the moon has traveled a little bit in its orbit, the moon is now somewhat east of the sun. And you could just see it setting just after sunset, and we are now in the waxing crescent phase. So we're going to let some more time go by. We're still well within waxing crescent. And as we get closer to first quarter, you're going to notice that the moon is rising later and later and later. So much so that by the time the first quarter phase actually arrives, the sun will be on the meridian just as the first quarter moon is rising. Let's take a look. So there's the sun on the meridian and the first quarter moon just rose. So that means when the sun sets, the first quarter moon's on the meridian, and then the first quarter moon sets around midnight. So now we're getting into the waxing gibbous phases. So we're going to let the moon just keep moving right along here. And when you notice that more and more light is getting added to the moon, and the moon is rising later and later and later. So now the waxing gibbous moon rises in the afternoon. Now, as we approach the full phase, notice that the moon is getting to the opposite side of the Earth. In other words, if you were standing, let's say, at the North Pole on Earth, you'd look in one direction and see the sun, and you'd look in the opposite direction and see the moon. So to put ourselves back in Baltimore, we're just going to watch, right now North America is in the night side of Earth. If you look at the inset, and now North America comes around and we're at the full moon. That means the full moon rises just at sunset. See there? So the sun just set and the full moon rose. So let's watch that again. So the sun sets and the full moon rises. That means the full moon transits the meridian at midnight, and the sun is now setting, and because we're now past the full moon, you will notice that the moon rises after the sun sets. So the moon is rising later and later, and it's going to be usually past most people's bedtime before any moon will rise, the waning gibbous moon. Interestingly, if we notice in the waning gibbous phase, the waning gibbous moon is rising very late at night, long after the sun is set. And that means it's setting long before the sun sets. So we have the waning gibbous moon setting sometime in the morning. And as we come up on third quarter, notice that we will have to wait until midnight. So there goes North America. And if you see our hometown coming at midnight, the third quarter moon just rises and the sun is up, and the third quarter moon sets at noon. So now we're getting into the waning crescent phases. let's watch now and see how the moon starts to catch up to the sun, you might say. You notice that it's still maintaining that eastward drift. We saw at the beginning that the moon was moving to the left on your screen, which is the eastward direction. But because the moon has now come around, so to speak, it's catching up and still moving in the eastward direction, but it's now getting closer and closer to the sun in the sky. Pretty soon, the moon comes back to its new phase, and therefore the new moon is going to rise with the sun, and it's going to transit the meridian approximately at the same time as the sun, and it'll set at sunset. So let's watch that now. And there we go. So a full lunar cycle as seen from our home. Now, if you listen to Pink Floyd's Dark Side of the Moon, you may have noticed that after the very end of the last track, there's a voice overheard that says, there is no dark side of the moon, really. As a matter of fact, it's all dark. And I think that's a great way to wrap up this presentation on the moon, because we have shown that there is no such thing as a dark side. In other words, yes, there is a dark side, but the near side of the moon is not always illuminated. Sometimes it's dark. So all the moon is dark at some point or another.